In today's video, we are going to define what a linear transformation is. And so a linear transformation is a mapping between two vector spaces that satisfy certain properties. We will also look at a couple properties of linear transformations, and we will show that two common operations studied in calculus are actually linear mappings. Given two vector spaces V and W, the mapping F, which maps V into W, which assigns a single vector f of u in W to every vector u in V, is said to be a linear transformation if these two conditions hold. First, f of u plus v is f of u plus f of v. And second, f of c times u is equal to c times f of u. The vector f of u is called the image of u under the transformation f. Right, now if f from v into w is a linear transformation, v and w are vector spaces, then these two conditions hold. F of 0 is equal to 0. F of cu1 plus so on and so forth plus cn un is equal to c1. This should be f of u1, right, plus so on and so cn f of un. So let's go ahead and fix that. This should be c1 f of u1 plus so on and so forth cn f of un. Now, here it's understood that this zero vector here is the identity in V, and this is the identity in W. And here it's understood that the scalar multiplication and additions of the two operations are in V, and here the two operations are defined as in W. All right, so proof of the first statement. Take a look at the identity in V. So I'm going to label that as 0 sub V. Well, we can multiply that by 0. Now, since it's a linear transformation, this is 0 times f of the V identity, which you should recall is the identity in W. All right, so that proves the first statement. The proof of the second statement is going to be left as an exercise. Let C prime A be, so we let this vector space here be this, or the set be the set of all functions whose derivatives are continuous on the closed interval AB. We're going to show that the differential operator d sub x defines a linear transformation from C prime to C. All right, so remember, this set here is the vector space of all continuous functions on the closed interval A to B. All right, so we let f of x, g of x be functions in C prime, A to B, and we're going to say k is some real number. All right, now define the differential operator. So this is a mapping from C prime into C. And it is d sub x of f of x is equal to f prime of x. So it's just the derivative. First, we have to show that the first property holds. So we take d sub x of f of x plus g of x. All right, so this is f of x plus g of x prime. And you should recall from calc that this is f prime plus g prime, right? This is the sum rule of derivatives. Well, that is dx of f plus dx of g. So the first property is satisfied. Second property, we take a look at dx of kf. Right, so this is k f of x prime. And again, from calculus, we get this is k times f prime of x. This is the constant multiple rule of derivatives, right? And this is just k times dx of f. So therefore, dx is a linear transformation. Or another term is known as a linear mapping. All right, both terms will be used interchangeably. Now we're going to show that the mapping H from the set of all continuous functions to the real numbers that is defined by H equals the integral from a to b of f of x is a linear transformation. All right, so again, let two functions, f of g, be in C minus infinity to infinity, so the set of all continuous functions. And we'll let k be some real number. So define this mapping by h of f of x equal to the integral from a to b f of x dx. Proof of the first property. All right, so we want h of f of x plus g of x. So this will be derivative from a to b f of x plus g of x dx. Okay? Now, from calculus, we know that the integral itself you can split across addition. So this is the same as this integral plus this integral. But that is h of f of x plus h of g of x. So the first property is satisfied. Second property, h of kf, right? So this is integral from a to b, k f of x dx. Well, again, from calculus, we know that we can essentially pull the constant out. So we can write this as k times this integral. But that is k times h of f. Both properties are satisfied, so we can therefore conclude that h from set of all constant or all continuous functions to set of real numbers is a linear transformation. If we have three vector spaces, v1, v2, v3, and we have two linear mappings, f from v1 into v2, and g from v2 into v3, then the mapping h, v1 into v3, that is defined as h of u equals g of f of u, is also a linear transformation. So if you take the composition of linear transformations, the result is still a linear transformation. First, right, so for any vectors u1 and u2 in V1, notice we have h of u1 plus u2 will be g of f of u1 plus u2. Right, but this will give us g of f of u1 plus f of u2. Right, notice that g of u1 and g of u2, f of u1 and f of u2, notice they are both in V2, right, because f maps from V1 to V2. Now notice that because f of u1 and f of u2 are in V2, and g is a linear transformation from V2 to V3, we'll get g of f of u1 plus g of f of u2. The first property is satisfied. Now if we take any real number k, look at h of k of u1. Right, well this will be g of f of k of u1, right, which is g of kf of u1, right? And of course, this is because that f is a linear transformation from V1 to V2. And again, we note that f of u1 is in V2. So now, g of k times f of u1 is k times g of f of u1. Again, because g is a linear transformation. But this is precisely k times h of u1. So the second property has been satisfied. Therefore, h from V1 to V3 is a linear transformation. So this proves that the composition of linear mappings is also a linear mapping. That concludes our introduction into linear transformations. And so, in this video, we defined what a linear transformation was, looked at a couple properties, and then saw that two common operations from Calculus 1, namely the derivative and the integral, are linear mappings. In the next video, we're going to look at two measures of a linear transformation known as the kernel and range. So those are sets. And then we'll look at measures that involve the kernel and range. So as always, I thank you so much for watching this video, and I will see you all in the next one.